Why is space freezing cold if the stars are so hot? You've probably noticed the paradox without ever stopping to chase it. The sun's surface burns at almost 6,000 Kelvin. The most massive stars run 10 times hotter. Trillions of these furnaces fill the universe, and yet a thermometer floating between them reads 2.5 degrees above absolute zero. The intuition that space is cold because it's far from the stars doesn't quite work. The answer is stranger, and tonight we're walking through it slowly. The mechanics, the engineering, the coldest place in the universe, and the long, dim future after the last star burns out. Get comfortable, hit subscribe, and settle in. Part 1. The question no one asks. Try this thought experiment for a moment. Imagine you could climb into a small spacecraft and fly straight up from the sun's surface, holding a thermometer out the window. You're starting in a place where the temperature reads about 5,772 Kelvin, hot enough to vaporize any solid material you can name. You'd expect, as you rise higher, that the temperature would drop steadily, falling off as you move away from the heat source. And in a way, it does. But within a few million kilometers, before you've even reached the orbit of Mercury, that thermometer would already be giving you readings colder than anywhere on Earth has ever been measured. By the time you've traveled out beyond the planets and into the open territory between stars, the thermometer would settle on a temperature of about 2.725 Kelvin. That's roughly 270 degrees Celsius below the freezing point of water, colder than Vostok Station in Antarctica on the worst winter night ever recorded, and not by a small margin, colder than the surface of Pluto by tens of degrees, colder than anything humans have ever encountered without the help of a laboratory. And the cold isn't subtle. We're not talking about a chilly afternoon. We're talking about a temperature where every gas you can name has long since liquefied or frozen solid. Oxygen freezes at 54 Kelvin. Nitrogen freezes at 63 Kelvin. Hydrogen, the lightest and most stubborn gas in the universe, freezes at 14 Kelvin. The temperature of the open expanse between stars 2.7 Kelvin is below all of those. Helium, which on Earth requires liquefaction temperatures around 4 Kelvin, behaves in genuinely strange quantum ways below that point. Cold at the level we're talking about doesn't just stop ordinary chemistry, it rewrites the rules of matter. The part worth slowing down for is what's happening on either end of that journey. The universe is not short on furnaces. Our sun radiates about 3.8 times 10 to the 26th power watts of energy every single second. In 1 second, the sun pumps out more raw energy than human civilization has consumed in its entire history. There are somewhere between 100 billion and 400 billion stars in the Milky Way galaxy alone. There are estimated to be roughly 2 trillion galaxies in the observable universe. Trillions of galaxies, each containing hundreds of billions of stars, every one of them firing energy outward in every direction continuously. And the room between them is the coldest place anyone has ever measured. So, the question is the one the title puts on the table, and it's a question worth taking seriously. How can a universe stuffed with heat sources have a thermostat that reads, on average, just barely above absolute zero? The first instinct most people have, when they think about this at all, is to say that space is just very far from the stars. That sounds reasonable. The night sky between stars is empty. Energy spreads out. By the time light from another star gets to you, it's faint. So of course it's cold out there, and there's something correct in that intuition. But it isn't quite the answer. The vacuum just outside the sun's photosphere, the vacuum a few hundred kilometers above the surface of the sun itself, is also extraordinarily cold by the same measure. The vacuum a meter above a roaring campfire on Earth is, in a certain sense, also cool. The campfire isn't really heating the empty space around it. It's heating the air. That's a clue. The real question isn't why space is cold. The real question is why the heat the universe is full of fails to warm space up. Once you frame it that way, the puzzle changes shape. We're not looking for a missing heater. We're looking for a process that fails. The universe contains rivers of energy. Somewhere between those rivers and the rest of the universe, something breaks down. Whatever that broken thing is, it's the answer. This video is about that breakdown. It's a long walk through some genuinely strange territory, and we're going to take it slowly. We're going to look at 4 things in turn. First, what the word temperature even means when you're in a vacuum. It turns out the everyday meaning of hot smuggles in some assumptions that fall apart in space. Second, we're going to look at the 3 highways heat normally travels along and find out that the universe has shut 2 of them down between stars, leaving only one fragile route open. Third, we're going to look at the strangest places, the coldest places, including a region of space colder than the leftover warmth of the Big Bang itself, and the inversion problem on the Sun, where the part farthest from the heat source is somehow hotter than the part closest. And fourth, we're going to look out into the long future, where the universe continues to cool toward equilibrium across a stretch of time so enormous that the entire history of stars will look, in retrospect, like a very brief candle. The thesis is simpler than the journey, and I want to plant it now so you can hold on to it through everything that follows. Heat needs somewhere to land. The universe gives it nowhere to land. That's the whole story, expanded out across 2 hours of evidence. Cold space is not the absence of heat. It's heat that has nowhere to go. And once you've absorbed that idea, the related questions start to line up. Why does the night sky look black, even though it's full of stars? Why does a satellite need so many radiators when it's sitting in what most people think of as a freezer? Why does the surface of the moon swing from baking to freezing in less time than it takes to brew a cup of coffee? All of these are the same question, asked from different angles. By the end of this video, they'll all line up the same way. Cold is what heat does when it can't go anywhere useful. There's another angle worth flagging before we go on. The night sky we see is not really a sky. It's the closest few hundred light years of our own galaxy, set against the much fainter background of everything else. If you could see in microwave wavelengths, you'd see the cosmic microwave background, that 2.7 Kelvin glow in every direction, smooth and uniform. The thing we call the night sky is the small foreground of nearby stars layered over an otherwise unbroken cold. You're never looking out into emptiness when you look up. You're looking into the freezing afterglow of the early universe with a few bright pinpricks in front of it. Before we get there, though, the first thing we need to do is take the word temperature itself apart. Because the difference between a spark from a welder and a cup of hot tea is the same difference, scaled up, that explains why the gas between the stars can be 1,000,000 Kelvin and still freeze your spacecraft. Part 2. What temperature means when there's nothing to touch. Picture a welder at work. They strike an arc, sparks fly, one of them lands on the back of their gloved hand. The temperature of that spark is around 1,000 degrees Celsius hotter than the inside of most home ovens, easily hot enough to set wood on fire, and yet the welder flicks the spark off and gets back to work without a flinch. Now picture a cup of tea, freshly poured. The tea sits at about 80 degrees Celsius, more than 12 times cooler than the spark on a per degree basis. Spill the tea on your hand and you'll be reaching for cold water and bandages. The everyday word hot is doing something sneaky here. It's running together 2 different ideas that physics distinguishes carefully. The first is temperature. Temperature is, in a precise sense, the average kinetic energy of the particles in a system. How fast are the molecules moving and bouncing around? That's temperature. The second is total thermal energy. How much energy, in total, is actually stored in the system? That depends on both the temperature and the amount of stuff. The spark is hotter on a per-particle basis, because each individual particle in that bit of molten metal is moving very fast, but there are almost no particles in the spark. It's a flake of metal smaller than a grain of sand. The total energy is trivial. By the time the spark touches your glove, the heat capacity of the glove can absorb the entire energy of the spark without raising the glove's temperature by more than a fraction of a degree. The tea, on the other hand, contains something like 10 to the 25th power particles per cup. Each particle is moving slower, but there are so many of them that the total energy is enormous. The tea has the heat budget to do real damage. This is the distinction we have to carry into space, because once you take it seriously, the word temperature starts to behave in counterintuitive ways out there. The solar wind that crashes against Earth's magnetic field every day has a measured temperature of hundreds of thousands of Kelvin, sometimes 1,000,000 or more. By the simple definition, average kinetic energy of particles that is hotter than the surface of the Sunday. But the solar wind is also extraordinarily thin, roughly 5 particles per cubic centimeter at Earth's distance. For comparison, the air you're breathing right now contains around 2.5 times 10 to the 19th power molecules per cubic centimeter. The solar wind is, by particle count, billions of times less dense than the most ordinary room you've ever been in. So is the solar wind hot? In one sense, yes. The individual particles are screaming with kinetic energy. In the sense that matters the sense of whether being inside it will warm something up, no, it isn't. A spacecraft passing through that hot plasma is bombarded by very fast particles, but there are so few of them that the heat flux from those collisions is negligible compared to what the spacecraft is losing by radiating into the dark on its own. You're a millionaire walking through a city of empty streets. The average wealth of the people on the block is gigantic, but the block is empty, and you can't bump into anyone to spend the money on. Temperature, without enough particles to carry it, is wealth without anyone to spend it with. Or, here's another way of seeing it. Imagine you fill a swimming pool with a few teaspoons of boiling water. Every other teaspoon of the pool is empty, vacuum, nothing. The teaspoons of boiling water are real, they're hot, but there are so few of them in the pool that if you dipped your hand in, you'd feel almost nothing. The pool isn't cold because the water you put in wasn't hot. The pool is cold because the hot water you put in didn't add up to anything. The interstellar medium, on the right scale, is exactly that. The plasma between stars is genuinely hot by the kinetic measure. There just isn't enough of it for that heat to matter to anything passing through. This same idea, in reverse, is what makes the sun's corona such a puzzle, and we'll get to it later. The corona sits at millions of Kelvin by particle measurement, but in some regions you could in principle fly a spacecraft through it without instantly being destroyed, because the particles are so sparse that the total heat flux to the spacecraft is manageable. The Parker Solar Probe, currently the closest object humans have ever flown to a star, is engineered around exactly this distinction. Its heat shield doesn't have to deal with the corona's temperature so much as with the corona's density and the sun's direct radiation. That's the missing piece in how we usually talk about temperature. We collapse hot into a single concept that includes both how energetic the particles are and how many of them there are. In a dense environment like an oven or a fire, those two things track together. The air is hot and there's plenty of it, so heat flows efficiently to your skin. In a sparse environment like the corona or the solar wind, the two come apart. The particles can be screaming hot by the speedometer measure, and the environment can still be functionally cold by the burning your hand measure. Everyday intuition collapses both versions into one word and gets confused as soon as it tries to ask about space. There is another way of talking about the temperature of space, and this is the one that determines whether you actually freeze. It's called equilibrium temperature. It's the temperature an object in a given location will eventually settle at given the radiation coming in from nearby heat sources and the radiation it's emitting back out. At Earth's distance from the Sun, the equilibrium temperature for a plain dark object, perfectly absorbing, perfectly emitting, comes out to about 279 Kelvin, which is 6 degrees Celsius, roughly a chilly fall afternoon. At Pluto's distance, that same object would equilibrate to about 44 Kelvin. Far beyond Pluto, away from any star at all, the only thing left to equilibrate with is the cosmic microwave background, and the equilibrium temperature drops to 2.725 Kelvin. That equilibrium number is what most people mean when they say space is cold. It's not the kinetic temperature of the sparse plasma drifting through. That can be hundreds of thousands of Kelvin. It's the temperature at which an object stops cooling because it's receiving as much radiation as it's sending out. And almost everywhere in the open expanse, far from stars, that number is freezing. So now we have two definitions of temperature, and you need to keep both of them in mind. The gas between the stars is hot in one sense and cold in another, and only the second one matters for whether you survive the trip. Heat is everywhere. Heat that can actually do something, that can warm a body, raise a thermometer, sustain a chemical reaction, exists only where there is enough matter close enough to deliver it. That brings us to the next piece. If temperature is about what particles can do to each other, what happens when there aren't enough particles to do anything at all? When you remove the medium, you don't just slow down heat transfer, you shut down 2 of the 3 highways heat normally uses to travel. Only one is left open, and as we're about to see, that one highway cannot make up the difference. Part 3. The 3 highways of heat. Take a moment and think about how you actually warm something up in everyday life. 3 different mechanisms are at work, and most of the time we use all 3 at once without noticing. Let me walk through them. The first is conduction. You stir a pot of hot soup with a metal spoon. After 30 seconds, the handle of the spoon is uncomfortable to hold. The heat from the soup has travelled through the metal of the spoon from one end to the other by direct contact between particles. Hot, energetic atoms at the soup end jostled their neighbours. Those neighbours jostled their neighbours. The jostling propagated up the spoon. That's conduction. It requires that particles touch each other and pass energy along by contact. The second is convection. You stand by a radiator on a cold day. The radiator heats the air right against its surface. That air, now warmer, expands slightly, becomes less dense, and rises. Cooler air flows in from below to take its place. The warm air spreads through the room, hits the cold window, gives up its heat, sinks, and the cycle repeats. That's convection. It requires a fluid, a gas, or a liquid that can flow and carry heat with it. The third is radiation. You sit by a window on a cold morning and the sunlight on your face feels warm, even though the air in the room is freezing. The sun has not touched you. There's no fluid carrying heat to you from the Sunday. The heat is arriving as electromagnetic waves, photons, in the infrared and visible spectrum that travel through 93 million miles of vacuum, then the atmosphere, then the window, and finally hit your skin. They're absorbed, the energy becomes heat, your face is warm. That's radiation. It doesn't need a medium. Light does the job by itself. Now here's the question that opens the door. Which of these 3 mechanisms work in space? Conduction needs particles in contact. In the gap between stars, a hydrogen atom typically travels for years, sometimes thousands of years, before hitting another atom. The density is so low that conduction effectively doesn't happen. The atoms are too far apart to pass heat to each other in any practical sense. Conduction is, for our purposes, shut off. Convection needs a fluid that can rise, fall, and circulate. In a near-perfect vacuum, there is no fluid. Nothing to flow, nothing to carry heat in bulk. Convection is shut off too. That leaves radiation, photons, light. They travel through vacuum without any need for a medium because they are themselves the medium. Light works just fine in space. That's why we can see the stars at all. Radiation is the only highway open between stars. And radiation is slow, lonely, and bound by geometry. We're going to dig into all three of those problems in the next act. But before we leave this idea, I want to plant one image in your mind that explains why this matters so much for everything that follows. You have probably owned a vacuum-insulated thermos at some point. A cheap one, a fancy stainless steel one, whatever. The whole design of those flasks is based on what we just said. Two walls of metal or glass separated by a thin gap. The air has been pumped out of the gap, so it's a near vacuum. Why does the design work? Because the vacuum gap shuts down conduction, since there's nothing to conduct through. It shuts down convection, since there's no fluid to circulate. The only way heat can escape the inner wall is to radiate across that vacuum gap to the outer wall, and radiation across short distances at moderate temperatures is slow. Hours later, your coffee is still warm. That's the universe's basic principle, expressed as a kitchen appliance. Now, flip the picture. A hot object in space is the coffee. Empty space is the thermos gap multiplied by trillions of kilometers. The object can still radiate, and it will, continuously, but it can only deliver heat to whatever its radiation actually reaches. If nothing is nearby, the heat goes out into the dark and just keeps going. The implication runs in both directions. A hot thing in space can shed heat slowly. A cold thing in space can gain heat only if something hot enough is shining on it. And the surfaces of the cold thing have to actually be facing the hot thing for the heat to land. There is no being warmed by ambient air. Because there is no ambient air, you either see a heat source or you don't. This is also the reason that, contrary to what Hollywood often suggests, a body exposed to vacuum doesn't flash freeze. Without conduction or convection to carry heat away, the body can only radiate, and radiation at human body temperature is slow. The danger of vacuum exposure isn't freezing, it's lack of oxygen, and the rapid depressurization of fluids inside the body. People who have briefly survived accidental vacuum exposure, there are a small number of documented cases, reported that the cold was the least of their problems. The asphyxiation, the boiling saliva on their tongue, the swelling of tissue, those came first by orders of magnitude. Slightly counterintuitive, given how often the freezing spaceman image shows up in movies, but the physics is unambiguous. Vacuum is hostile in many ways, and cold is the slow part of the menu. There's a small piece of history worth mentioning here. The vacuum flask itself was invented in 1892 by Sir James Dewar, a Scottish chemist working at the Royal Institution in London. Dewar was studying the liquefaction of gases. He was the first person to successfully liquefy hydrogen in 1898, and he needed something to keep his cold liquids from boiling off too quickly. The double-walled glass flask he designed solved the same problem, in miniature, that the entire universe solves for cold matter. Strip away conduction and convection by removing the medium between two surfaces, and radiation is all that's left. The Dewar flask is the physics of interstellar space in a piece of laboratory glassware. Bring this back to the central thread for a beat. Heat exists in space. It exists in immense quantities. The universe is overflowing with photons and energetic particles. What the universe lacks is the medium that lets heat travel by anything other than light. Without conduction, without convection, every heat transfer in space becomes a story about radiation. Radiation is the only car on the highway, and the highway, as we're about to see, is not flat and direct. It's a sphere that grows so fast that a single car has almost no chance of arriving anywhere in particular. That spherical geometry is the next piece. But before we get to the inverse square law itself, I want to spend some time on a place where you can actually watch this physics happen in real time. Every spacecraft humans have ever flown has had to solve the problem of heat in vacuum, and the way they solve it is the central thread of this video made physical. Part 4. How a star actually throws heat into nothing. Picture, for a moment, what's happening inside the Sun right now. Down in the core, hydrogen is fusing into helium under pressure and temperature. So extreme, about 15.7 million Kelvin, that protons can overcome their mutual electrical repulsion and stick together. Every fusion reaction releases a small amount of energy in the form of photons. Those photons are born inside the Sun, and what happens next is one of the most surprising slow-motion journeys in physics. A photon born in the Sun's core does not just shoot straight out. It hits another particle almost immediately, gets absorbed, and is re-emitted in a random direction. Then it hits another particle, gets absorbed, re-emitted, on and on, hundreds of thousands of times. The photon's actual path through the Sun is a random walk, taking step after step in random directions, gradually working its way outward by sheer statistical drift. Some estimates suggest it can take a photon anywhere from tens of thousands to hundreds of thousands of years to travel the 700,000 kilometers from the Sun's core to its surface. The sunlight warming your skin at this exact moment may have been born inside the Sun during the Pleistocene ice ages, slowly bouncing its way toward the photosphere across thousands of human lifetimes. Once it reaches the photosphere, though, everything changes. The Sun's photosphere is the layer where the gas becomes thin enough that photons can finally travel freely without being immediately reabsorbed. From the photosphere outward, a photon leaves the Sun at the speed of light and travels in a straight line until it hits something. The 8 minutes between the photosphere and your retina are nothing. The slow part was the 100,000 years getting through the Sun in the first place. What's the Sun actually doing then on a continuous basis? It's producing photons in its core, randomly walking them outward through its interior and releasing them into vacuum at its surface. Roughly 3.8 times 10 to the 26th power watts of energy radiated continuously in every direction away from the surface. Imagine a balloon expanding around the Sun at the speed of light. Every second, a new shell of photons leaves the surface, all moving radially outward. That's how a star throws heat into the universe. Now here's the part that connects to the Stefan Boltzmann law, which is the rule that governs all of this. The hotter a surface, the more violently it radiates. And not linearly, the rate of radiation rises as the fourth power of temperature. Double the surface temperature, and you get 16 times the radiated power. Triple it, 81 times. The most massive stars in the Milky Way, the O-type giants, have surface temperatures up to 50,000 Kelvin, nearly 9 times hotter than the Sunday. Their radiated power per square meter is something like 60,000 times what the Sun puts out. They burn through their hydrogen in a few million years and die early. This radiation law also applies to you. Your body, at about 310 Kelvin, or 37 degrees Celsius, is constantly radiating in the infrared. The rate works out to roughly 100 watts of heat going out from your skin in all directions continuously. You are a 100-watt incandescent bulb made of meat. The reason you don't cool down to room temperature in minutes is that, on Earth, you're surrounded by air at room temperature that's also radiating back at you, and the difference is small. In space, with nothing radiating back at you, you'd cool faster. Still not instantly, but faster than on Earth. Here's another implication that surprises most people. Every object you can see, including yourself, is constantly radiating. The fork on your dinner table is radiating. The wall behind you is radiating. The chair you're sitting in is radiating. All of them are giving off photons at a wavelength determined by their temperature. The wavelength is what changes really cold objects radiate in the far infrared, room temperature objects in the mid-infrared, hot stoves in the near-infrared, glowing red iron in visible red light, the sun's surface in visible light biased toward yellow-green, and the hottest stars in ultraviolet. The spectrum of radiation is a kind of universal thermometer. Point an infrared camera at anything and you can read its temperature directly from the wavelength of the light it's putting out. The same physics that lights the sun and warms your hands also produces the most uncomfortable property of radiation in space. When a photon leaves a hot object, it carries some of that object's energy with it. To do useful work to warm something else, that photon has to hit something. If it never hits anything, it just travels, getting longer and longer in wavelength as the universe stretches it, until it's effectively part of the background radiation. Most photons from most stars never hit anything for the entire age of the universe. They just travel through what we, looking from the inside, call the night sky. Take a moment with that. Right now, photons from stars you'll never identify are streaming through every cubic centimeter of the room you're sitting in. They've been traveling for thousands or millions of years to arrive here. They pass through the air, through the walls, through your body, and out the other side without leaving any noticeable mark. Most of them will keep going for the rest of the lifetime of the universe, traveling and never being absorbed by anything that cares. The universe is, by this measure, almost transparent. Most photons aimed at most directions just keep going. That's not because the universe is empty of matter, it's because the matter is too sparse, too cold, too perfectly arranged in the wrong way for those photons to land. Bring it back to the thread. This is the universe's only mechanism for moving heat across distance. Photons traveling alone in straight lines, hoping to be absorbed by something that can use them. Stars are not heating space. They are firing photons into a sphere whose surface area grows the moment those photons leave. We can already see where this is going. If a photon's job is to deliver energy to a surface, and there are very few surfaces between stars to deliver to, then most of the universe's photons are doing nothing useful. How fast does the geometry actually work against us? How quickly does the intensity of a star's light fall off as you walk away from it? The answer is one of the cruelest equations in physics, and we'll get to it in a moment. Before we do, though, we need to look at a more concrete demonstration of everything we've covered so far. Every spacecraft humans have ever flown has had to solve this exact problem on a tighter budget, and the way they solve it is the central thread of this video made physical. They roast on one face and freeze on the other, just a few feet apart, in vacuum because heat in space cannot get around obstacles. That's where we're going next. Part 5. Sunburn and frostbite on the same body. The argument I keep returning to in this video is that heat in space is a story about what surfaces can see, not about how much heat exists. Nowhere is that more visible than on the metal skin of every spacecraft humans have built. So I want to spend some time here, because once you see this physically, once you see the temperatures on a single body in orbit, the rest of the video stops being abstract. Take the International Space Station. As of this recording, the ISS has been continuously inhabited since November 22nd, 2000. It orbits Earth at an altitude of about 400 kilometers, making one full lap every 90 minutes or so. As it orbits, it spends roughly half of each lap in direct sunlight and half in Earth's shadow. The thermal environment outside is, in a word, brutal. A surface on the sunlit side of the station can reach about 121 degrees Celsius, which is about 250 degrees Fahrenheit, hot enough to instantly boil water, hot enough to cause severe burns on contact. A surface on the shaded side of the station, in Earth's shadow, drops to about negative 157 degrees Celsius, or negative 250 Fahrenheit, colder than any natural temperature on Earth, far colder than Antarctica's worst. Sit with that for a moment. Two surfaces, both on the same metal structure, separated by a few meters of vacuum, and they're 278 degrees Celsius apart. The same heat-conducting metal, if it was sitting on Earth, would equalize those temperatures within seconds because the heat would flow from the hot side to the cold side along the metal. In space, that flow is slow enough that the surfaces stay locked in their separate worlds. Each surface is dealing with what its face sees. Conduction along the structure is fighting a losing battle against radiation in and radiation out. And because the ISS orbits every 90 minutes, every external component cycles through that 278-degree swing roughly 16 times a day, every day, for decades. Imagine the thermal stress that puts on bolts, seals, electrical connectors, joints, solar arrays. Engineers spend years choosing materials that can survive cycles like that. Aluminum alloys, composite panels, multi-layer insulation. Most consumer products would fatigue and fail in weeks. The blankets you see in every photo of a spacecraft, the gold and silver foil sheets that wrap the outside, are not insulation in the everyday sense. They're not designed to keep air from carrying heat away, because there is no air. They're designed to control radiation. Each layer is a very thin, reflective film. When sunlight or thermal radiation hits the outer layer, most of it is reflected back into space. A small fraction passes through to the next layer, which reflects most of it back. By the time radiation has worked its way down through 5 or 10 or 20 layers, depending on the application, almost none of the original energy is left. The same trick works in reverse for keeping heat inside. The blankets are a controlled radiation pipeline, nothing more. Now, here is something most people don't realize until they think about it. The ISS, like every crewed spacecraft, has a chronic overheating problem, not a freezing problem. Astronauts give off body heat. Computers run hot. Life support equipment, especially the components that scrub carbon dioxide and process water, generates heat continuously. All of that heat has to go somewhere. On Earth, convection takes care of it without us noticing. In space, with no air to carry it, every joule has to be radiated out through specifically engineered surfaces. Look at any picture of the ISS and you'll see, mounted between the solar arrays on giant mechanized trusses, a set of large white panels. Those are the radiators. Together they cover roughly 1,800 square meters, about half the playing surface of a basketball court, devoted purely to dumping heat into the dark sky. The radiators have to be carefully oriented. They can't face the sun, because the sun would heat them up faster than they can shed. They can't face the warm Earth directly, because Earth's thermal infrared emission would warm them too. They have to be pointed into the open expanse of dark sky, where the cold equilibrium temperature is only a few Kelvin and the panels can radiate efficiently. Inside the station, a fluid loop carries waste heat from where it's generated racks of electronics, the crew quarters, the life support equipment out through cold plates that absorb the heat, then through pipes that snake out along the truss to the radiator panels. Anhydrous ammonia is the working fluid in the external loop. The fluid arrives at the radiators warm, the radiators emit photons into open sky, the fluid cools, and the cycle continues. If the loop ever fails, if a leak develops, or a pump stops working, the inside of the station starts climbing past habitable temperatures within hours. The astronauts have to put on emergency cooling garments or evacuate. That's just the station. Now consider the James Webb Space Telescope, which began science operations in 2022 and has been delivering data ever since. The Webb sits at the second Lagrange point, about 1.5 million kilometers from Earth on the side opposite the Sunday. Its job is to look at the universe in infrared, which means its instruments have to be extraordinarily cold, colder than any infrared they're trying to detect, or their own thermal glow would drown out the signal. To keep the instruments cold, the Webb has a sun shield. It's 5 layers of aluminized polyimide film, each layer about as thin as a human hair stretched taut across an area roughly the size of a tennis court, about 21 meters by 14 meters when fully deployed. The sun-facing side of that shield reaches a temperature of about 383 Kelvin, which is 110 degrees Celsius. The side facing the instruments, the shaded side, sits at about 36 Kelvin, which is negative 237 degrees Celsius. That's a temperature drop of 347 degrees Celsius across a few meters of vacuum, maintained passively. With no active cooling, nothing more than 5 tightly stretched films and the geometry of what each film can see. Why 5 layers, specifically? Because of how radiative cooling actually stacks. Each successive layer can only radiate heat to what it can see. The first layer sees the sun on one side and the second layer on the other, so it absorbs solar energy and radiates a portion of it forward into open sky while passing only a fraction to the second layer. The second layer receives that smaller fraction, radiates most of it out the sides into open sky, and passes an even smaller fraction to the third layer. By the fifth layer, the residual heat is so small that the layer can radiate it efficiently into the dark, and the instruments behind the shield are protected. The math of the stack is the core of the central thread of this video. Heat has to go somewhere. The Webb's engineers calculated, layer by layer, exactly how to route the heat into the open sky beyond. Each film is a mirror that hands the heat off to its neighbor or sends it sideways into the dark. Without conduction, without convection, every joule has its path planned in advance. There's one more layer to the Webb story that doesn't get talked about much. The mirror itself isn't quite cold enough on its own. The MIRI instrument, the mid-infrared instrument, which observes in the longest infrared wavelengths the Webb is sensitive to, needs to be even colder than the rest of the telescope. The passive cooling provided by the sun shield gets the optics down to about 36 Kelvin, but MIRI needs about 6 Kelvin to function. So the Webb has, in addition to the sun shield, an active cryocooler, a small refrigeration unit running off the telescope's electrical power, using cycling helium to drag the MIRI detectors down those extra 30 Kelvin. The active cooling is the smallest, lowest power refrigeration system ever flown in space, and it lets the Webb see further into the cold infrared than any telescope before it. I want to pause here and connect this back to the question we started with. Why is space cold? Because, on the scale of a spacecraft, heat can only go where surfaces can see. The Webb's instruments are sitting in vacuum at 36 Kelvin while 5 meters away. On the other side of those films, the sun is hammering the first layer at 383. The temperature of space is meaningless without knowing what direction you're facing. The sun-facing direction is roasting. The away-from-sun direction is freezing. The same physics that gives the universe its general dark cold also gives a spacecraft these absurd local extremes. Now go the other direction. The Parker Solar Probe, launched in 2018, is the closest object humans have ever sent toward the Sunday. In December of 2024, it completed its closest approach, yet about 6.1 million kilometers from the Sun's surface, which is well inside the solar corona. Most of the spacecraft, including the science instruments, are at room temperature throughout the mission. That sounds impossible. The front face of its heat shield routinely reaches about 1,371 degrees Celsius, which is 2,500 degrees Fahrenheit. The instruments are 2.5 meters behind that shield, sitting at the same kind of temperature you'd find in a typical office on Earth. How? Same principle. The thermal protection system, that's the official name of the carbon composite shield, is shaped and pointed so that the instruments behind it never see the sun directly. They only see the back of the shield. The back of the shield is not nearly as hot as the front, because the front radiates most of its absorbed solar energy back into space from its sun-facing side. The sun-facing side experiences about 475 times more solar flux than what Earth receives, and most of that flux is reflected or re-radiated outward, away from the instruments. Only the small fraction that conducts through the carbon composite ever reaches the back, and the back is at a moderate enough temperature that the instruments are fine. The Parker Solar Probe survives by hiding. It hides in the geometric shadow cast by its own shield. The shield doesn't keep the sun from being hot. It keeps the instruments from being able to see the Sunday. That distinction is the whole video in miniature. Every spacecraft does some version of this. Every working satellite, every orbiter, every robotic probe, every crewed module is a thermal engineering project disguised as a science mission. The orbital mechanics and the instruments are downstream of solving the question of where to put the heat. Where can it go? What can it see? What surfaces are facing the sun? What surfaces are facing the dark? And how do we engineer the structure so that the right things are warm and the right things are cold? I want to spend a moment on the human scale version, because it's easy to forget that astronauts on spacewalks are facing this exact problem with their own bodies as the spacecraft. An astronaut on an extravehicular activity is wearing what NASA calls an extravehicular mobility unit. Direct sunlight outside the protection of Earth's atmosphere is brutal, sometimes more than 1,300 watts per square meter of incident solar energy, depending on where in orbit they are. Solar heating, plus the body's own metabolic heat, plus the heat generated by physical exertion, would cook the astronaut within minutes if it weren't actively removed. Under the pressure suit, every astronaut wears a liquid cooling and ventilation garment, basically long underwear made out of mesh fabric with 90 meters of fine plastic tubing woven through it. Chilled water is pumped through that tubing across the astronaut's skin, absorbing body heat, then carried back to the suit's life support pack. There, a device called a sublimator handles the disposal. The sublimator has a slow leak of water into vacuum. As the water hits the vacuum, it flashes into ice, then immediately sublimates from ice directly into vapor. That phase change absorbs an enormous amount of energy. The latent heat of sublimation and the vapor drifts off into open space, carrying the heat with it. I want you to picture this for a moment. A human in orbit, holding their core body temperature within survivable limits by spraying water into the dark. The vapor never lands on anything, it just travels. A small cloud of ice crystals carries away the heat of a working human body, photon by photon and molecule by molecule, into the open expanse beyond. Every astronaut who has ever done a spacewalk has, in a literal sense, donated their body heat to the universe at large. That image, more than any equation, is the central thread of this video in one sentence. Heat in space goes where it can go. The dark is large enough to take it. The astronaut on the spacewalk is finding the dark with one little vapor cloud per second of work. Failure modes are instructive. In 2013, astronaut Luca Parmitano was on an EVA when a problem with the cooling loop caused water to leak into his helmet. The water didn't go to vapor as designed. Instead, it pooled and began floating around inside his suit in microgravity. He couldn't see, couldn't hear well, and was at risk of inhaling water. The crew had to abort the spacewalk and get him back inside. The temperature control system in those suits is so finely tuned that any failure in either direction becomes a survival emergency. Too little cooling and the astronaut overheats. Too much liquid water in the wrong place, and they can drown in zero gravity. The line between functional and lethal is narrow. Apollo astronauts on the lunar surface had it worse in some ways. Daytime surface temperatures on the moon can reach about 127 degrees Celsius. The suits they wore had to handle direct, unfiltered sunlight on the visible side and the cold lunar shadow on the rear, sometimes within a half-step transition as they moved between sunlight and shade behind a boulder or a piece of equipment. The suits dealt with this in real time, the cooling water flowing constantly, the sublimator working continuously, all of it monitored from the ground. There's an additional twist on the Moon that doesn't apply in Earth orbit. The lunar dust on the surface absorbs sunlight extraordinarily efficiently, and when astronauts walked on the Moon, that dust stuck to their suits in fine layers. Mission planners on Apollo 17, the last crewed lunar mission, reported that the astronauts came back inside the lunar module looking like they'd been working in a coal mine. The dust was so absorbent that suits returning from EVA were measurably warmer than they should have been. The dust was acting as a black body coating, raising the suit's external temperature in sunlight. Future lunar missions will have to design around this problem. Reflective coatings that work on Earth do not stay reflective on the Moon. The dust dulls them within hours. There's also the issue of soft components. The fabric outer layers of Apollo suits stiffened in the lunar shadow as temperatures dropped, then loosened back up in sunlight. The visors had to be coated with a thin gold film, which reflected solar infrared back while letting visible light through. Even the air pressure inside the suit was a thermal consideration. Too much pressure, and the suit became rigid and hard to bend. Too little, and the temperature differential pushed the seals harder. Every part of the suit was solving some piece of the heat problem. The pattern is everywhere you look. Every successful crewed mission, every working satellite, every robotic probe that has lasted longer than its initial commissioning has solved this problem in its own way. Some by hiding from light, some by exposing themselves to light at carefully chosen angles, some by deploying enormous engineered radiators, some by stacking films and letting geometry do the work. One more example that often gets overlooked. The Mars rovers, Curiosity, Perseverance, the older ones too, operate in a thermal environment that swings from about minus 140 degrees Celsius at night to about 20 degrees during the day at the equator. They survive these swings using radioisotope thermoelectric generators that produce both electricity and continuous waste heat. The waste heat is deliberately routed through the rover's chassis to keep the electronics warm during the cold Martian nights. On the warmer side, when the rover would otherwise overheat from solar exposure plus the radioisotope source, plus exertion of the wheels, heat exchangers shed the excess into the thin Martian atmosphere and into the open sky at night. The rovers are running a delicate thermal accounting on a world where neither sky nor ground gives them much help. Bring it all the way home. Everything we've talked about on this scale, the ISS, the Webb, the Parker Solar Probe, the EVA suit, the sublimator is the universe at large operating on a budget that's been worked out by engineers. The universe doesn't have engineers. The universe just lets the physics happen. The cold gap between the Earth and Mars, the cold gap between the Sun and Alpha Centauri, the cold gap between every star and every other star, all of that is the same physics, just without anyone designing it. Heat radiates from one place, travels through nothing, and lands wherever its geometry allows. Most places, that's nowhere, so most places stay cold. Every spacecraft in orbit right now is performing the same trick that the universe does naturally, but with intentional design. The radiators have to be pointed away from the sun, in just the way that interstellar space happens to be pointed away from any nearby star. The instruments have to hide in shade, in just the way that the dark gap between galaxies has always been in the shade. The cold side of the spacecraft is the cold side of the universe. The hot side of the spacecraft is wherever the nearest active heat source happens to be reachable. The whole physical picture out there, from a single satellite to an entire galaxy, behaves the same way. That brings us back to the geometric question I promised earlier. We've talked about how heat moves only by light, with no medium to help. We've talked about how a single hot object can simultaneously roast and freeze depending on which surface you measure. What we haven't done yet is look at the unforgiving geometry of light spreading out across the open expanse, the inverse square law. The reason a star is essentially invisible from a couple of light years away That's where we're going next, and it's where the question of why space is cold gets its sharpest answer. Part 6. The inverse square law and the loneliness of light. Light leaving a star spreads in every direction at once. Picture a single photon flicked off the surface of the sundae. It travels in a straight line that one photon does. But the sun is producing photons in every direction, so, on average, the photons fan out across an expanding sphere centered on the star. As that sphere grows, it has more surface area. The number of photons in the sphere doesn't change. So the photons per square meter, what physicists call the intensity, has to drop. Here's the math in plain terms. The surface area of a sphere is 4 pi times the radius squared. If you double the radius, the surface area becomes 4 times what it was. Triple the radius, 9 times the area. Tenfold the radius, 100-fold the area. The intensity of light at any point on that sphere drops as 1 divided by the square of the distance. Double your distance from a light source, and the brightness drops to 1/4. Tenfold the distance, 100-fold dimmer. 100-fold the distance, 10,000 times dimmer. The geometry is unforgiving. Apply it to our solar system. At Earth's distance, 1 astronomical unit, about 150 million kilometers from the Sun, solar irradiance averages about 1,361 watts per square meter. That's the solar constant, roughly the power of an oven element burning on every square meter of Earth's upper atmosphere. Plenty to warm a planet, drive weather, run ecosystems, sustain liquid water across most of the surface. Now step outward. At Mars, 1.52 astronomical units from the Sun, the intensity drops to about 590 watts per square meter, less than half of Earth's. Mars is colder than Earth, and dimmer in daylight than most people imagine. At Jupiter, 5.2 astronomical units out, the solar intensity is about 50 watts per square meter, comparable to the light a few hours after sunrise on a cloudy day on Earth. At Saturn, 9.5 astronomical units, the figure is around 15 watts per square meter. At Uranus, just under 4. At Neptune, about 1.5. At Pluto, averaging 40 astronomical units, under 1 watt per square meter. Pluto's noontime sky, when New Horizons flew past in 2015, was about the brightness of moonlight on Earth. The Sun is a small bright pinpoint there, not a disk. Keep going. At the heliopause, where the Sun's outflowing solar wind meets the interstellar medium around 120 astronomical units from the Sun, the intensity drops to a small fraction of a watt per square meter. By 1,000 astronomical units, the Sun is still bright enough to see with the naked eye, but its warming effect on a passive object is essentially zero. By 10,000 astronomical units, the Sun is one of countless points of light in the local sky. By 100,000 astronomical units, about 1.5 light years, you're halfway to the nearest star, and the Sun is just another star. Proxima Centauri sits 4.24 light-years from us, which is roughly 268,000 astronomical units away. The intensity of sunlight at Proxima's distance is about 1.4 times 10 to the negative 9th power watts per square meter, a billionth of 1 watt. A face turned toward our Sun at that distance would intercept less power than a mosquito wing absorbs from a candle. The Sun is still there, still pumping out the same 3.8 times 10 to the 26 power watts every second, but to anything at Proxima Centauri, that energy might as well not exist. Now plant the image. From Proxima's perspective, our Sun is just another bright point in a sky full of bright points. It's still radiating, it's still hot, it just doesn't matter to anything at that distance. The geometry has won. Our galaxy has stars spaced typically about 5 light-years apart on average, with much greater distances common in the outer disk. So the probability that any given cubic meter of interstellar space is close enough to a star for that star's radiation to meaningfully warm something there is vanishingly small. The Milky Way is mostly empty. Pick a random point in the galaxy, and you're, on average, several light years from the nearest source of heat. Whatever radiation reaches that point from all the surrounding stars combined is a tiny fraction of what any one of those stars produces at its surface. A useful mental picture. Think of each star as a grain of sand. Our Sun is one grain. The next nearest grain, Proxima Centauri, would be about 100 kilometers away on the same scale. 2 grains of sand, separated by 60 miles of nothing, firing photons at each other. The geometry of intensity says that almost none of the photons, either one fires, will hit the other. Between any 2 grains of sand, the photons are doing nothing. They're traveling and getting redshifted and aging, but they aren't warming anything. The intergalactic version is even worse. Galaxies are themselves separated by tens of millions of light years on average. The Milky Way and Andromeda, our 2 nearest large galactic neighbors, are about 2.5 million light years apart, which is close on the cosmic scale. Most galaxies are far further apart than that. Photons leaving one galaxy that happen to be aimed at another galaxy travel for tens of millions of years just to arrive. The space between galaxies is even darker and even colder than the space between stars within a galaxy. This is the modern resolution to Olber's paradox, by the way. The old question, if the universe is full of stars in every direction, why isn't the night sky uniformly bright? Why is it dark? The answer turns out to involve everything we've discussed. The universe is finite in age, so light from the most distant stars hasn't had time to reach us. What has reached us has been stretched by cosmic expansion, redshifted out of the visible into infrared and microwave. And the inverse square law means that even where stars do exist, their light is diluted into nothing across the enormous distances involved. The dark night sky is, in a way, the physical proof of every claim in this video. The universe is full of stars and the night is dark because the geometry is fatal to heat at distance. There's an additional reason the night sky is dark that's worth mentioning. The redshift caused by cosmic expansion doesn't just shift light from distant sources, it weakens it. A photon traveling across the universe loses energy as its wavelength stretches. Light from the most distant galaxies is dimmed not only because they are far away, but because the expansion of space has redshifted their photons all the way out of the visible band into infrared, microwave, or longer. So even the light that does reach us from far away is colder, weaker, and harder to see than it would be in a static universe. The universe is actively cooling and dimming its own night sky in real time, faster than any new starlight can fill it back in. Bring it back to the central thread for a beat. Stars are not heating space. They are firing photons in every direction. The photons travel in straight lines. The sphere of photons grows according to the inverse square law, and almost all of those photons hit nothing for the entire age of the universe. The heat of a star is real, but it disperses across a sphere whose area explodes so fast that beyond a relatively short distance, the heat might as well not exist anywhere except locally. Heat needs somewhere to land. The open expanse between stars provides almost nowhere to land. We've talked about the mechanics, we've talked about the engineering, we've talked about the geometry. Now we need to ask the next question, which is what happens in the regions farthest from any heat source at all, the places no star is shining on, the places stranded between galaxies. Is there a floor under which the universe will not cool? It turns out there is, and the floor itself has a name and a discovery story and an unexpected dent in it where one anomalous nebula has gone even lower. That's where the next act takes us. Part 7. The Cosmic Microwave Background, the Floor of Cold. In 1964, 2 radio engineers at Bell Telephone Laboratories in New Jersey were trying to track down a noise problem. Arno Penzias and Robert Wilson had been assigned to a horn-shaped antenna originally built for early satellite communications. They wanted to use it to study faint radio emissions from astronomical sources, but to do that they needed to characterize and eliminate every source of interference. There was a persistent low background hiss they couldn't account for, not at any particular frequency, just a steady, soft static present in every direction they pointed the antenna. They tried everything. They considered the city of New York and pointed the antenna away. They considered the Earth's heat. They examined the antenna itself. They climbed inside it. They found a pair of pigeons had been nesting in the throat of the horn and removed both them and the droppings they had left behind. The hiss remained. After all the work and the pigeons, the noise was still there, the same in every direction, all the time. About 65 kilometers away in Princeton, a team led by physicist Robert Dicke was working from the other direction. They had been calculating what should be left over from the Big Bang. If the universe really began in an extraordinarily hot, dense state and had been expanding and cooling ever since, then the leftover photons from that hot period should still be floating around, redshifted by the expansion to longer and longer wavelengths. By their calculations, those photons should now be detectable as a uniform bath of microwave radiation at a temperature only a few degrees above absolute zero. They were getting ready to look for it. When Penzias and Wilson described their stubborn hiss to a colleague, the colleague connected them to Dick. Dicke and his team realized, with a mixture of excitement and disappointment, that Penzias and Wilson had already accidentally detected exactly what they were preparing to search for. The phrase Dicke is reported to have said to his team was, "Boys, we've been scooped." That accidental hiss was the cosmic microwave background, and its discovery essentially settled the question of the Big Bang. Penzias and Wilson got the Nobel Prize in 1978. The hiss is still there. In every direction you can point an antenna in the sky. Let me explain what the CMB actually is, because the word afterglow gets thrown around, but the physics behind it is more interesting than the catchphrase. About 380,000 years after the Big Bang, the universe had expanded and cooled enough that protons and electrons could combine into neutral hydrogen atoms. Before that, the universe was a hot, opaque plasma free electrons everywhere, scattering any photon that tried to travel any distance. After recombination, photons were suddenly free to move without immediately being absorbed. They've been traveling ever since, stretched by the expansion of space into longer and longer wavelengths, dropping in energy along the way. Today, those photons are everywhere, in every direction, at almost exactly the same temperature. The most recent reanalysis of European Space Agency Planck mission data published in early 2025, using the new N-pipe pipeline and combining the result with the older COBE-FIRAS measurements from the 1990s, places the temperature of the CMB at 2.72548 Kelvin, with uncertainty of about 5/10,000ths of a Kelvin, about 270.4 degrees Celsius below the freezing point of water. One of the most precise temperatures ever measured in physics. This is, for our purposes, the floor. Anywhere in the open expanse of space, if an object is given enough time to equilibrate and is not being heated by anything else nearby, it will eventually settle at about 2.725 Kelvin. Not absolute zero, just barely above it. That's the natural temperature of the universe in a region with no local heat source. The sun, the stars, the dense knots of matter that produce planets and galaxies, those are local exceptions to the floor. Out across most of space, by volume, 2.725 is what you get. Let that sit. The leftover heat from the Big Bang is what keeps the universe from being at absolute zero everywhere. Without it, every cubic meter of space far from a star would be at 0 Kelvin, and the universe would be even colder than it is. The CMB is the universe's last memory of its own birth, smeared evenly across every direction in the sky, holding the floor up at just under 3 degrees above true zero. The density of CMB photons is enormous, roughly 411 photons per cubic centimeter throughout the entire observable universe. There are more CMB photons in your living room right now than there are stars in the Milky Way. There are more CMB photons in a cubic meter of space than there are atoms in a cubic meter of the intergalactic medium. The universe has plenty of photons and barely any matter, but the energy each CMB photon carries is tiny, about 6 times 10 to the negative 24th power joules. Compared to the energy in a visible light photon from the sun, the CMB photons are vanishingly weak. You'd need to collect something like 10 to the 20th power CMB photons to feel any warmth at all from them. They're everywhere. They barely do anything. They just hold the floor. And the floor is slowly sinking. As the universe continues to expand, the CMB photons are stretched to even longer wavelengths, dropping in temperature. At the moment of recombination, the CMB was around 3000 Kelvin orange hot, glowing visibly. By 900 million years after the Big Bang, it was about 20 Kelvin. Today, 2.7. In about 100 billion years, it will be a fraction of a Kelvin. In a trillion years, almost indistinguishable from zero. The floor itself is on a slow slide downward, and we are catching it during one of the warmer phases of its long descent. There's something philosophically strange about all of this. The CMB is essentially a photograph of the cosmos at the moment it first became transparent. Every direction in the sky shows us a slightly different snapshot of the early universe. The tiny temperature variations across the CMB, on the order of 1 part in 100,000, are the seeds from which every galaxy that exists today grew. The CMB is both the architecture of structure and the floor of cold, 2 things in the same dataset. There's a 30-year history of refining the CMB measurement that's worth pausing on. The first detection was Penzias and Wilson's HISS in 1964. The first detailed map came from NASA's COBE satellite in the early 1990s, which confirmed that the CMB was almost perfectly uniform and which earned its principal investigators the Nobel Prize in 2006. WMAP, the Wilkinson Microwave Anisotropy Probe, operated from 2001 to 2010 and refined the maps further, pinning down the geometry and age of the universe to within a few percent. The ESA Planck mission, 2009 to 2013, produced the most detailed CMB map yet, and its data is what physicists are still mining in 2025. 3 generations of spacecraft, each one taking the universe's temperature with more precision than the last, tie back to the thread. Any object placed in the open expanse of space, given enough time, radiates heat into the dark until it equilibrates with the CMB. At that point, it is still radiating, but it's also receiving exactly as much radiation back from the cosmic microwave background as it's sending out. Equilibrium. That's the natural temperature of the universe, far from any star, and it's about 2.7 Kelvin, freezing by any reasonable measure, 270 degrees Celsius below the freezing point of water. And this is the universe at its calmest, in the regions least disturbed by anything. So this should be the answer. The CMB is the floor. Nothing colder, right? That's what the textbooks would suggest, and for almost every region of the universe, it's true. Except almost. There's one place where the floor breaks. One place where matter, by its own motion, has cooled itself below the leftover heat of the Big Bang. Somewhere out there, a dying star has engineered a region colder than the universe itself. It shouldn't be possible by the simple logic of the floor. It is possible, and the way it happens is the central thread of this video pushed to its most extreme form. That's where we go next. Part 8. The Boomerang Nebula, colder than the universe itself. I want to be careful with this section, because it's the central thread of the whole video pushed to its sharpest point. Everything we've talked about so far has been about heat that can't reach a place. The boomerang is something different. The boomerang is about heat that is reaching a place. The CMB photons are physically passing through the boomerang's gas right now, but the place is cooling faster than the heat can warm it. The leftover warmth of the Big Bang is right there, and it's losing the race. The object itself sits about 5,000 light-years from Earth in the southern constellation Centaurus. In optical images, it looks like a soft pair of glowing lobes, a bipolar shape that earned the nebula its name in 1980, from Australian astronomers Keith Taylor and Mike Scarrett, who thought the shape was vaguely reminiscent of a boomerang. It's not what astronomers would describe as visually spectacular at first glance, a pale curl of light against the dark of the southern sky. Most photographs render it as a faint blue mist, sometimes processed to bring out the structure of the lobes. But the boomerang is a pre-planetary nebula, meaning it's a star in the middle of dying, and the way it's dying is unusual. A few thousand years ago, a star at its center, in the late phases of its life as a red giant, ejected its outer atmosphere. Most red giants do this, slowly, over tens of thousands of years, in a relatively gentle process called the asymptotic giant branch phase. The boomerang's central star did not do it gently. It blew material outward at speeds over 100 kilometers per second, about 10 times faster than typical red giant winds. The cause was almost certainly a binary companion. A second, smaller star, possibly around 1.5 solar masses that had been orbiting the red giant, began spiraling inward through the giant's puffy atmosphere. As it did, it dumped enormous amounts of energy and angular momentum into the ejection, driving the giant's outer layers outward at extreme speed. The ALMA observations, published in 2024, refined this picture further. A common envelope phase, sometimes called a brief stellar merger, in which the two stars effectively fuse their atmospheres before the outer material is blown clear. Common envelope evolution is one of the more dramatic processes in stellar physics, and it's been a subject of serious study since the 1970s. When a binary star system contains stars of different sizes, and the larger star expands into a red giant, its outer atmosphere can swell to engulf the smaller companion. Once that happens, the companion finds itself orbiting inside the giant's atmosphere, dragging through the gas. The drag pulls the companion inward and dumps enormous amounts of orbital energy into the surrounding gas. In some systems, the companion eventually merges with the core of the giant. In others, the orbital energy is enough to blow the giant's atmosphere clear, leaving a tightly bound binary or a single dense remnant with an expanding shell. The Boomerang Nebula appears to be a case where the second outcome happened, with the additional violence that gives the ejection its unusual speed. The result was a violently expanding shell of gas, about 10,000 times the mass of Earth, flung outward at a speed sufficient to cross the entire continental United States in roughly 1 minute. That's the ejection. Now, the surprising part. As that gas expanded into vacuum, it cooled, not slightly, catastrophically. Let me explain why. In plain language, because this is the physics that makes the boomerang what it is. When a gas expands without absorbing energy from its surroundings, the work it does, pushing outward, has to come from somewhere. It comes from the gas's own internal energy, the kinetic energy of the molecules bouncing around inside it. As the gas expands, the molecules give up some of their kinetic energy to do the work of pushing outward, and they slow down. Slower molecules means lower temperature. The gas cools. This is the same physics that makes a can of compressed air feel cold when you spray it. The gas inside the can is at room temperature, but as it suddenly expands into atmosphere, it does work against itself, and the resulting cool gas chills the can. Squeeze the trigger long enough, and the can frosts over. Same effect, except the boomerang's ejection was about 10,000 times the mass of Earth, expanding into pure vacuum where nothing could push back. With no nearby radiation field strong enough to warm it back up, the gas expanded, it cooled. Then it kept expanding, and it kept cooling. Over about 1,500 years, the boomerang's expanding shell cooled to about 1 Kelvin, about 1.7 degrees colder than the cosmic microwave background. As far as anyone has been able to detect, this is the coldest natural place in the observable universe. The discovery story is worth telling. In 1995, astronomers Raghvendra Sahai and Lars Oak Nyman used the Swedish ESO submillimeter telescope in Chile to observe the boomerang in radio frequencies. They were looking for the spectral signatures of carbon monoxide molecules, a common species in the cool gas around dying stars. They expected to see emission lines, the molecules glowing in the millimeter wavelengths because they were warmer than the surrounding background. What they saw was the opposite. The carbon monoxide molecules were absorbing CMB photons rather than emitting any. The only way that's possible is if the gas surrounding the molecules is colder than the CMB itself. Because absorption versus emission depends on the temperature difference between the medium and the photon bath, if the medium is colder, it absorbs. If it's warmer, it emits. The CO lines in the boomerang were dark against the CMB. When Sahai and Nyman worked out the numbers, the temperature came out to about 1 Kelvin. The result was so unexpected colder than the natural floor of the universe that it took years for the astronomy community to fully accept it. The early proposals included various error sources. Maybe the line modelling was wrong. Maybe the dust composition was different than assumed. Maybe the geometry was misinterpreted. Each one was checked and ruled out. The boomerang really is below the CMB. Subsequent observations with ALMA, the Atacama Large Millimeter Array, refined the picture considerably. A 2013 paper by Sahai and colleagues mapped the nebula at unprecedented resolution. The bipolar structure turned out to be more complex than the optical images suggested, with a younger, narrower outflow embedded inside the older, broader lobes. The 2024 update further constrained the mass loss history and confirmed the binary interaction model. I want to pause and let the strangeness of this land, the leftover heat of the Big Bang, fills the entire universe. It's the natural flaw that everything cold eventually equilibrates to. Out in the open territory between galaxies, every passive object drifts toward 2.7 Kelvin, and that's it. Yet here, in one specific corner of the Milky Way, there is a region of space where the flaw has been broken, where matter is colder than the photons surrounding it, where the photons of the Big Bang itself are warming the gas, slowly, while the gas continues to cool itself faster than the photons can put heat back in. Hour by hour, the CMB is gently pushing the boomerang's gas back up toward 2.7 Kelvin. In tens of thousands of years, assuming the expansion eventually slows enough that the cooling stops outrunning the heating, the boomerang will lose its anomaly and equilibrate with the rest of the universe. For the moment, it's a pocket of below cosmic floor, cold, sustained by the lingering work the gas is still doing as it expands. There's a small visual paradox to mention. The boomerang appears in optical photographs as a soft glow because dust grains in the nebula reflect light from the central star. So visually, optically, it looks like a bright nebula. Thermally, it's the coldest known place in the universe. The visible photograph and the thermal reality are two completely different stories about the same object. If your eyes worked in millimeter wavelengths instead of optical, the boomerang would look like a hole in the sky against the warm glow of the CMB. Now, pull the thread tighter, because this is what I've been building to. The boomerang is proof that cold in space is not about how much heat is available. It's about whether heat can keep up with whatever is removing it. The CMB photons are right there, passing through the boomerang's gas, ready to warm it. The gas is moving away from equilibrium faster than the slow radiative process can drag it back. As long as the gas keeps expanding fast enough, it stays cold. Once it slows down, it equilibrates upward and the anomaly closes. The same physics, in slow motion, is what makes the rest of the universe cold. The expansion of cosmic space stretches the CMB photons and cools them. The expansion of the early Big Bang did the same thing on a much faster timescale. Everywhere in the universe, matter and radiation are doing some version of the same dance, equilibrating, cooling, expanding, redistributing energy. The boomerang is just the most extreme local example, where the cooling rate has temporarily overwhelmed the warming rate. Compare it to the lab record, briefly, because I think it sharpens the contrast. The coldest temperature ever created in a laboratory was 38 picokelvin, that's 38 trillionths of a degree above absolute zero, achieved in 2021 by a German team using the Bremen drop tower. The experiment involved ultra-cold rubidium atoms in a Bose-Einstein condensate, manipulated during the few seconds of microgravity that the drop tower provides. That's an extraordinary achievement, far colder than the Boomerang Nebula by many orders of magnitude. The lab record, though, lasted for a fraction of a second under exquisitely controlled conditions designed by humans specifically to push toward the coldest possible state. The boomerang has been below the CMB for over 1,000 years, sustained by nothing more than its own physics, with no engineers involved. That's worth marking. Humans, with deliberate effort and very sophisticated equipment, briefly created something colder than the boomerang for a fraction of a second. The boomerang, with no help from anyone, has been below the natural cosmic floor for 1,500 years and counting. There's something philosophically nice about that. Human laboratory physics requires layers of sophisticated engineering, magnetic traps, evaporative cooling, free-fall chambers, ultra-stable lasers to briefly produce ultra-cold conditions for fractions of seconds. The universe, with nothing but a dying star and a binary companion in the geometry of vacuum, produces a 1,000-year cold zone as a side effect of stellar mass loss. The boomerang isn't trying to be cold. The cold is what falls out of the physics when matter expands fast enough into the dark, without the help of any engineer to push the conditions. The universe gets to those temperatures by accident. Speculation, clearly flagged. Is the boomerang the only such object? Almost certainly not. The boomerang was found because of an unusually clean line of sight, an unusually violent ejection, and a careful set of millimeter-wave observations. The galaxy almost certainly contains other pre-planetary nebulae undergoing similar adiabatic cooling processes. They're harder to detect against the CMB background, but the class of sub-CMB objects likely contains other members. We just haven't picked them all up yet. Surveys with the James Webb Space Telescope and the Atacama Large Millimeter Array are gradually mapping more pre-planetary nebulae, and the catalogue of cold outliers will probably grow over the next decade. It's also worth noting that the boomerang is, in some ways, less rare than it appears. The galaxy contains roughly 10,000 known planetary nebulae, with many more thought to be hidden behind interstellar dust. A significant fraction of those probably went through ejection histories not too different from the boomerangs. The reason most don't show sub-CMB temperatures today isn't that they never did, it's that the cold phase doesn't last long. The boomerang has been below the CMB for about 1,500 years and will probably be back at equilibrium within tens of thousands more. We are, in cosmic terms, catching it during a brief flash. Catalogue dozens of other pre-planetary nebulae in detail, and you'll probably find several caught at the same stage. There's a related set of objects, sometimes called protoplanetary nebulae, or pre-PN stars, in the very brief transition period between the asymptotic giant branch and the main planetary nebula phase, when the central star is still cool enough not to ionize its surrounding gas, but the ejection is already happening. The boomerang is unusually well studied because it's relatively close and has a clean line of sight, but its physical state is shared with many siblings out across the galaxy. The boomerang also raises interesting questions about what counts as the temperature of the universe. If a region of matter can locally be below the CMB, then the universe isn't really at a single uniform temperature. It has pockets above and below the floor, depending on whether matter is being heated or is doing work against its surroundings. The CMB is a floor in the sense that, given enough time and no other input, everything will equilibrate to it. But enough time can be hundreds of thousands of years, and during that time, dynamics can drive local matter well above or just below the floor. I want to bring this back to the thread one more time, with the volume turned up. Why is space cold? Because the universe is mostly empty, and heat in the universe travels only as light, and the geometry of empty space dilutes light to almost nothing across the distances involved. That's the basic answer. But the boomerang takes it one step further. Even when the CMB photons are present, even when there's leftover heat from the Big Bang threading through every cubic centimeter of an object, the object can still be colder than that heat if the object is cooling itself faster than the heat can arrive. Cold in space isn't just about absence. It's about rates. Matter that does work against itself fast enough drops below whatever floor the surrounding photons would otherwise hold it to. That's the lesson of the boomerang in a single sentence. Cold is what matter does when it can outrun the photons trying to warm it. The Big Bang's leftover warmth isn't a strong enough heater to keep up with a violently expanding shell of gas. Most of the time, in most places, the cosmic photons win. The boomerang is the exception that proves the rule, because it shows that the rule is about rates, not absolutes. And there's a flaw under the flaw we should at least mention briefly, because it makes the picture complete. The CMB isn't the very last word on what empty means. Even if you could somehow shield a region of space from all radiation, all matter, all CMB photons, could you reach absolute zero? It turns out you couldn't, and the reason has nothing to do with photons or stars or any of the things we've discussed. It has to do with the quantum mechanical structure of vacuum itself. The empty of physics is a more complicated word than it sounds. We'll touch on this only briefly, but it deserves a moment. Part 9. Quantum vacuum and zero-point energy. Imagine you could build a perfectly sealed box, evacuate every molecule of gas from inside it, shield it from every photon, cool it to as close to absolute zero as your equipment could manage. Inside that box, what's left? The answer is not nothing. Quantum field theory, the framework physicists use to describe how particles and forces actually work, predicts that even a perfectly evacuated region of space contains a kind of background activity that can never be turned off. The fields that fill the universe, the electromagnetic field, the various quantum fields that produce particles, never truly settle. They jitter. Pairs of virtual particles continuously appear and annihilate in matched pairs, balancing the energy books too quickly to be directly observed, but leaving measurable consequences for anything sensitive enough to detect them. The Casimir effect is the experimental proof. Take two metal plates, place them very close to each other in a high vacuum, suspend them so they don't touch. The plates restrict which virtual particle wavelengths can exist between them, only wavelengths that fit in the gap. Outside the plates, all wavelengths are allowed. The imbalance in zero-point activity on either side produces a tiny but measurable inward force, pushing the plates together. Hendrik Casimir predicted this in 1948. It was first directly measured in 1997, and the precision has been steadily improving since. The implication for our central question is what matters here. there's a flaw under the flaw. The CMB sets the lowest temperature an object in equilibrium can reach. The quantum vacuum sets an even lower flaw, a residual quantum activity that exists regardless of temperature, regardless of any heat source, regardless of whether you can see any stars from where you are. But that flaw cannot be tapped as useful heat. The energy is real, but you can't run a heat engine on it because the second law of thermodynamics requires a temperature difference between hot and cold reservoirs, and there is no colder reservoir than the quantum vacuum. Periodically, ideas circulate in popular media about harvesting zero-point energy as a free energy source. Mainstream physics rejects this not because the energy isn't there, but because there is no temperature gradient to extract it from. You need somewhere colder than your source to dump your entropy, and the quantum vacuum is the coldest sink there is. So bring it back to the thread for the brief connection this part is meant to make. The quantum vacuum reinforces the central lesson. Having energy and having heat available to deliver to something are not the same thing. The universe contains plenty of energy in every form. What the cold gap between stars lacks is the gradient that turns that energy into heat for anything sitting in it. From the largest scales, the inverse square dilution of starlight over light years, down to the deepest theoretical flaw, the zero-point activity of empty quantum fields, the same lesson holds. Cold is about whether heat can flow somewhere it can actually do useful work. In space, the answer is almost always no. Part 10. The Sun's Corona Problem. I want to come back to the Sun for a moment, because the Sun itself contains a stranger version of the question we started this video with. The title asked, how space can be cold when stars are hot. The Sun answers a sister puzzle in its own atmosphere. The part of the Sun farthest from its heat source is somehow hotter than the part closest to it. Heat is supposed to flow from hot to cold. On the Sun, in one specific layer, it appears to flow the other way. Let me walk through the temperature profile of the Sun, because the strangeness only lands when you see the numbers together. The Sun's core, where fusion happens, sits at about 15.7 million Kelvin. From the core outward, through the radiative zone, and then the convective zone, the bulk of the Sun's interior, the temperature gradually drops, as you'd expect. Energy produced in the core is slowly transported outward, and by the time the energy reaches the surface, the photosphere, the temperature has fallen to about 5,772 Kelvin. So far, so intuitive. The interior is hot, the surface is cooler. Now keep going outward. Just above the photosphere is the chromosphere, a thin layer where the temperature dips slightly at its base to about 4,000 Kelvin, then begins climbing again. Above the chromosphere is what solar physicists call the transition region, a layer only a few hundred kilometers thick, where the temperature explodes by orders of magnitude, climbing from tens of thousands to hundreds of thousands of Kelvin across that thin slab. Above the transition region is the corona, the Sun's outer atmosphere, which sits at a steady 1 to 3 million Kelvin, with some active flare regions briefly reaching 10 to 20 million. Stop and let that sink in. The surface of the Sun is about 5,800 degrees. The atmosphere above the surface is millions of degrees. Imagine standing next to a campfire and finding that the air 10 feet above the fire is 500 times hotter than the fire itself. That's roughly the magnitude of what's happening on the Sun, every moment, all the time. This isn't a footnote. It's one of the great open problems in solar physics, and it has a name, the coronal heating problem. Heat is supposed to flow from hot to cold. The corona shouldn't exist at the temperature it does, given the physics of conduction and radiation alone. Something is dumping energy into the corona faster than it can radiate that energy away, and the source can't be the photosphere directly, because the photosphere is too cool to do the job. Two leading hypotheses exist, both consistent with everything we've discussed about the central thread of this video. The first is wave heating. The Sun's surface is a turbulent, boiling sea of magnetic field lines and plasma, all in constant motion. Magnetic disturbances at the surface launch waves up along the field lines, specifically what plasma physicists call Alfvén waves, named after Hannes Alfvén, who first described them theoretically in 1942. These waves carry energy upward into the corona. As they travel up into the thinner, less dense plasma above the photosphere, they steepen, break, and deposit their energy as heat. The Parker Solar Probe, in operation since 2018, has measured dramatic switchback features in the solar wind that match what wave heating models predict. The Daniel K. Inouye Solar Telescope, which came online in 2020 and is the largest solar telescope ever built, published the first direct measurements of coronal magnetic field strengths in 2024, data that's now being used to constrain how much corona heat actually comes from waves. Recent work has also been done on what happens to the corona during solar flares, short bursts of activity, in which magnetic reconnection releases a colossal amount of stored magnetic energy in a few seconds to minutes. Coronal mass ejections, which can drive material out into the solar wind at speeds exceeding 2,000 kilometers per second, are the most extreme example. During a flare, local coronal temperatures can spike to 10 million Kelvin or higher, and the resulting energy is what produces the X-ray and ultraviolet emission that telescopes like the Solar Dynamics Observatory have been mapping continuously since 2010. Flares aren't the steady-state corona, but they're a magnified version of the same physics magnetic energy being deposited into a thin medium faster than the medium can radiate it away. The second is nanoflare heating. The corona is laced with magnetic field lines that constantly tangle and reconnect. Every time two field lines reconnect, they release a tiny burst of energy, a nanoflare, a billionth or so the size of a typical solar flare. Each one is microscopic, but the corona is covered in them all the time. Add up enough microscopic energy releases, and you get a steady supply of heat. The IRIS satellite and the Hinode mission have been spotting bright points and rapid brightening events for years that are consistent with the nanoflare picture. Most solar physicists now think both mechanisms operate, with the relative contributions shifting depending on the type of magnetic environment. Quiet sun coronal holes seem to favor wave heating. Active regions seem to favor nanoflares. The boundary between the two is one of the things current solar missions are trying to nail down. Notice the contradiction with intuition and bring it back to the central thread. We started this video assuming heat flows outward from a heat source. The sun's interior fits that picture cleanly. By the time you've passed the photosphere, though, the source of the corona's heat is no longer the core. It's the magnetic field itself, acting at the surface and above. The corona is hot because magnetic energy is being deposited there, in a region where the matter is too thin to radiate the heat away efficiently. Conduction and radiation aren't keeping up with the rate of energy injection, so the energy accumulates as temperature. Now connect it carefully to the central question. The corona is hot for the same kind of reason that the open expanse between stars is cold. In both cases, what determines temperature isn't the proximity of a heat source by itself. It's the balance between the rate at which a region can accumulate energy and the rate at which it can shed energy. Open space sheds heat into the dark faster than any distant star can deliver it, so it stays cold. The sun's corona accumulates magnetic heat faster than its sparse plasma can radiate it away, so it stays hot. The same underlying physics, the relationship between matter density, radiation efficiency, and energy input, produces opposite results depending on which side of the balance you're on. The corona also shows you that the geometry of heat in space isn't simple. We started with the assumption that hot equals close to a source and cold equals far from a source. The corona breaks that assumption inside a single star. Lab plasma physics offers a useful parallel. In fusion experiments, Researchers regularly produce hot plasmas at temperatures of tens of millions of Kelvin in tokamaks and stellarators. The plasma is hot because the magnetic field is being used to contain and heat it. The walls of the containment vessel, just centimeters away from the plasma, sit at room temperature. The walls aren't dramatically melted by neighboring million-degree gas because the plasma is too sparse to deposit much heat on contact. The same principle holds on the sundae. Magnetic confinement creates a hot region next to a cool surface, with the temperature gap maintained by density and geometry rather than by distance. The atmosphere of the Sun is hotter than its surface, even though the corona is further from the energy-producing core. Energy doesn't just flow downhill in temperature here, it gets deposited in a region by a separate physical mechanism, and the temperature reflects that input plus the slow rate of removal. The coronal heating problem is one of physics' last big unresolved puzzles, in the sense that we don't yet have a fully quantitative model that explains every observation. New solar telescopes, DKIST, Parker's Solar Probe, ESA's Solar Orbiter, are gathering data at a pace that suggests the problem will be substantially settled within the next decade. For now, it's worth pausing on a curious truth. Even the simplest question about a star, why is its atmosphere hot, turns out to be a story about exactly the same physics that makes space cold elsewhere. The same balance between input and output, between energy availability and energy removability, runs through every part of this picture. If even a single star defies the intuitive picture of heat, if the geometry of warm and cold isn't intuitive even at the Sun's own surface, what about the much larger cold pockets of the galaxy? The dark stretches where the only matter for hundreds of light years is the occasional hydrogen atom. The pockets of stable, persistent cold that hold themselves at low temperatures by radiating microwaves into the dark. The molecular clouds. We have one more piece to mention before we look out at the long cold future of the universe, and the molecular clouds are it. Part 11. Dark molecular clouds. The Boomerang Nebula is a violent outlier gas cooled below the cosmic floor by an unusually fast ejection. But quieter pockets of cold are spread throughout the galaxy, much less extreme, much more common. These are the molecular clouds. And the galaxy is, in a sense, full of them. A molecular cloud is a region of interstellar gas where hydrogen has cooled enough to form molecular hydrogen rather than remaining as free hydrogen atoms. They're often hundreds of light years across and contain tens of thousands of solar masses of material. Some, like the Orion Molecular Cloud Complex, are visible to amateur telescopes as dark patches against brighter background regions of stars. Others, like the Taurus Molecular Cloud, are sprawled across degrees of the sky. They're some of the coldest stable environments in the galaxy, outside of dying stars. Typical molecular cloud temperatures run from 10 to 20 Kelvin. Cold, compared to the equilibrium temperature, an object would have just sitting in interstellar space, where the CMB pins the asymptote at 2.7 Kelvin. Not below the CMB, molecular clouds are warmer than the absolute floor, but only by a small margin, and very much colder than the warm parts of the galaxy where stars are shining. The cooling mechanism is worth a sentence. As atoms and molecules in the cloud collide, they radiate energy away as microwaves, specifically through the rotational and vibrational transitions of molecules like carbon monoxide, hydrogen cyanide, and ammonia. The cloud sheds heat efficiently in the radio spectrum. Without nearby stars to heat it back up, the cloud cools to a steady floor where energy lost to radiation balances the slow gain from cosmic rays and from the CMB itself. The most famous examples are stellar nurseries. The Taurus Molecular Cloud, the Orion Molecular Cloud Complex, the Lupus Clouds, the dark, dense cores in L1544 and L1689 that the James Webb Space Telescope mapped in 2024. Each one is a region where the cold temperatures and high gas density allow gravity to slowly draw material together into protostars. Every star that exists, including our Sun, was born in one of these cold pockets. Cold is the womb of stars. The universe doesn't make hot stars in hot regions. It makes hot stars in cold regions by gravitational collapse, where the temperature is low enough that molecular hydrogen can survive and gather into dense knots. Bring it back to the thread. The galaxy is full of these long cooling pockets. Cold is the norm. Warm regions are the exception, sustained by active heat sources by stars that are currently burning, by gas that has been recently heated by some local process. Wherever a heat source switches off, a star dies, a flare fades, a cloud drifts out of a stellar nursery, and away from young hot stars, the temperature falls quickly toward the long natural floor. The galaxy isn't sprinkled with cold spots between warm regions. It is mostly cold, with warm regions being temporary local exceptions wherever a star is currently delivering radiation to nearby matter. That's the picture at the galactic scale. Now I want to widen the frame one more time to the entire universe and the entire arrow of time, because the final piece of the story is what happens when the warm exceptions run out. Part 12. The long cold future. The story so far has been local. A star here, a nebula there, a cloud somewhere else. Now I want to widen the frame to the whole universe and the entire arrow of time, because the final piece of this story is what happens when the temporary warm regions run out. The universe is expanding. As it expands, the CMB cools. As it expands, intergalactic gas gets sparser. As it expands, the average distance between heat sources increases, and the geometric problem of getting heat from a star to anywhere it might do work grows steadily worse. The cosmic timeline of cooling is one of the most thoroughly studied predictions of modern physics, and it stretches across timescales that exhaust ordinary language. Today, aged 13.8 billion years. The CMB sits at about 2.7 Kelvin. Stars are still forming in molecular clouds across the universe. The stelliferous era, the age of stars, is in full bloom. This is the time we live in, and from our perspective it feels permanent. From the universe's perspective, it's the briefest possible early phase. 100 billion years from now, cosmic expansion will have carried most galaxies beyond each other's observable horizons. The local group of galaxies, the Milky Way, Andromeda, the Triangulum, and several smaller satellite galaxies will have merged into a single elliptical galaxy, sometimes informally called Milkomeda. The rest of the universe will be invisible from inside this galaxy, receding faster than light because of the geometry of expanding space. From inside the merged galaxy, the night sky will be full of stars belonging to that one galaxy, and beyond it, nothing observable but the lingering CMB, now stretched to colder than 1 Kelvin. 1 trillion years from now, star formation is winding down. The gas reservoirs available in galaxies have mostly been used to make stars. What's left is too thin and too dispersed to form new ones efficiently. The brightest stars, the massive blue giants that burn through their hydrogen in a few million years, have been gone almost since the universe began on this scale. The most common stars in the universe, red dwarfs, are still slowly burning, but they too are running through their hydrogen. The sky is dimming, slowly, century by century, across timescales no living being could ever notice. By 10 to the 14th power years, that's 100 trillion years, the last red dwarfs are exhausting their fuel. Star formation has essentially ceased. The universe is dotted with cooling stellar remnants, white dwarfs, neutron stars, black holes, and almost no active fusion is happening anywhere. The CMB has dropped to a fraction of a Kelvin. The stelliferous era ends. The light is going out. By 10 to the 40th power years, white dwarfs have radiated away most of their stored heat and become black dwarfs, cold stellar remnants, drifting through an even colder galaxy. The CMB is so cold by then it's practically indistinguishable from absolute zero in any sense that matters. Neutron stars have cooled to the same fate. The universe is full of dim, cold objects and very little else. By 10 to the 100th power years, and stop and try to picture that number for a moment, a 1 followed by 100 zeros, even black holes evaporate. Stephen Hawking showed in 1974 that black holes slowly emit thermal radiation through quantum effects at their event horizons, gradually losing mass over enormous timescales. Stellar mass black holes evaporate in roughly 10 to the 67th power years. Just for context on these timescales, consider what they mean. 10 to the 67th power years is so much longer than the current age of the universe that the ratio between them is bigger than the ratio between a single human heartbeat and the entire current age of the universe. We are nowhere near the middle of cosmic time. We are at the beginning of it, in a phase so early that almost everything still works the way our intuition expects. Long after the last star burns out, the universe will continue cooling for stretches of time that make the current 13.8 billion years look like nothing at all. Supermassive black holes at the centers of dead galaxies last much longer, but eventually they too release the last of their mass as low-energy photons and disappear. After that, the universe is filled only with photons of vanishingly low energy and the occasional stray particle, all of it spread so thinly that the concept of temperature loses most of its meaning. The phrase heat death doesn't mean a fiery end. It means equilibrium. Everything has cooled to the lowest possible value. No temperature differences anywhere. No usable energy gradients. Nothing left for any process to do. The universe is at peace, and at zero, near as makes no difference. The arrow of time, which physicists describe as pointing in the direction of increasing entropy, completes its long journey. The maximum entropy state is reached. After that, no more change. I want to come back to the central thread one last time with the weight of the whole video behind it. The reason space is freezing cold today is the same reason it will be freezing cold forever. Heat needs somewhere to land. The universe is mostly empty, and as it expands, it becomes more empty. The places where heat can collect stars, planets, dust clouds, dense regions of gas are temporary local oases. Switch them off, and the long, natural cold reasserts itself. The CMB has been cooling for the entire age of the universe and will keep cooling for as long as the universe exists. Cold is the default. Warmth is the exception. Some speculative physics has even gone further. Roger Penrose has proposed, in his conformal cyclic cosmology framework, that the truly distant future of the universe, when all matter has decayed and only stretched-out photons remain, might in some mathematical sense be equivalent to the beginning of a new universe, with the same low entropy structure that ours started with. Most physicists treat this as fringe, but the idea sits as a quiet reminder that the questions raised by cosmic cooling go further than just thermodynamics. Other speculative scenarios involve what are sometimes called Boltzmann brains, random thermal fluctuations in the late cold universe that briefly assemble themselves into structures complex enough to think a thought before, dissolving back into noise. Most physicists also treat this as fringe, but not crazy. A grounding observation then. We, the viewer, this video, every human who has ever lived, every animal alive on Earth, right now, exist during the briefest possible bright window in the history of the universe. Cosmic time is measured in scales, where the stelliferous era is a moment near the beginning. The dark, cold equilibrium will outlast everything we know by factors that exceed our ability to write down in ordinary notation. The numbers are so large that the universe of stars is statistically just a flicker. Make the existential point gently, because this is a question worth holding rather than rushing through. The question, why is space cold, is really the question, why is the universe the way it is? The answer is that cold is what the universe is naturally, and at rest. Warm is what happens during this temporary stretch near the beginning, while there is still hydrogen to burn, while there are still gradients to exploit, while the geometry still occasionally allows heat to land somewhere useful. The cold isn't the absence of warmth. The cold is the steady state. The warmth every fire you've ever sat near, every sunset, every star in the night sky, is the strangeness. We've spent 2 hours unpacking what that means. Heat needs somewhere to land. The universe gives it almost nowhere to land. The brief exception is us, right now, in this thin slice of cosmic time when the stars are still burning and the energy is still flowing. Outside of that, in every direction and every time, the universe is freezing. It has been since the early seconds after the Big Bang stretched the first heat thin. It will be for the entire enormous future after the last star goes out. The night sky is dark because the geometry is fatal to heat at distance. The CMB is freezing because the leftover warmth of creation has been stretched and stretched until it can barely warm anything. And the long future is cold because cold is what the universe always wanted to be. Settle into that thought for a moment before you go. Every fire you've ever seen, every sunset you've ever watched, every star in the night sky above you, they are anomalies. They are the universe's brief, beautiful disagreement with its own nature. And the part of you that finds them beautiful is the part of you that knows, somehow, that they aren't going to last.